say you've had steak and chips for dinner or something, okay? Now, if you've had steak and chips for dinner and you're really full, and the waiter or waitress comes along and says, do you want more chips? Do you want more steak? You go, oh no, I'm gonna puke, right? So we all have had that feeling. But yet, when the chocolate cake comes, you'll eat it. So why is it specific for the chocolate cake? I've just been locked away in a room, apparently, because 100 years ago, someone tried to run away. But anyway, I'm a geneticist by trade. And the interesting thing is when you are asked what disease you study. And because people study genetics for any number of different reasons. You can do it for a nerdy reason. I mean, and that's perfectly, I'm a nerd. I mean, this is by definition. But a lot of people use it to study diseases, okay? Because how better to understand how something works than when something is broken? And that's the whole point. And so when you're talking about a disease, and I say I study obesity, which is what I study, is genetics of obesity, immediately I become the bad person. And the reason why I'm a bad person is because I'm perceived to give obese people, fat people, overweight people, okay, used all non-pejoratively, an excuse. Okay, I mean, that's, so this is an interesting point. I mean, philosophically, does that mean if you study the genetics of any disease, you are actually giving someone an excuse? But, you know, that's rather broad. I'm going to fix today on obesity, but specifically on body weight, and that's what I'm going to be talking to you guys about today. And I want you to consider the next, I don't know, 50 or 55 minutes, a rebuttal to that statement about whether or not I'm giving anyone an excuse when I'm actually trying to understand, they're only trying to understand their biology. So, are your genes to blame when your genes don't fit? And I think it's a first question I should actually ask. So, how many people here think your genes are to blame when your genes don't fit? And don't be shy. Oh my God, okay, all right. And how many people don't think your genes are to blame when your genes don't fit? This lecture is for you. But somewhere in the middle, the answer's in the middle. Obviously the answer, but that's no fun. No one likes gray. People like black and white. All right, so here we go. All right, I think part of the problem with dealing with body weight is that we have all got really quite fixated about it. And I think we have, and I don't think that's lying. So, leaving aside religion and philosophy, okay, for the moment, let's assume that these are our prime directives in life, okay? So we have to find and to eat food, clearly. We have to somehow avoid becoming food. This is important, right? There is the reproductive element. We have to survive long enough to reproduce, and you kind of repeat the process, right? At some point you fail, and then you become an living creature. And these prime directives are the same for every single living organism, no matter how many cells you're made of, 1 all the way to trillions. This is what has driven us all the way till now, okay? Now, clearly, in today's environment, when we do our foraging, it's slightly less dramatic, okay? But they come with their own obstacles, okay? So I worked at Addenbrooke's Hospital in Cambridge, and Marks and Spencer's, other supermarkets are available, opened one of these, Marks, I forgot what it's called, they're sandwich shops. So pardon? Thank you, Simply Food. So it's the Simply Food. It doesn't sell knickers, it doesn't sell underwear, it just sells food. So, and I was there with the whole rest of the hospital, it felt like, getting lunch one day. Okay, so this is a true story. And in front of me, shall we say, there was a lady. She may have been a doctor, she may have been a nurse. She was there in civis, so I don't know. But she was plus size. Okay, she was a large lady, and she had started her whole lunchtime foraging expedition with all of the best will in the world. Right? She had in her hand a yogurt, and she had a salad. And if she had been able to pay for the goodies she had just picked up right there and then, she would have walked out with what she wanted for lunch because that was her plan, okay? But clearly that is not what happens, because what happens? You have to get in line, the IKEA line, the Disneyland line, okay? And everywhere in the world that I have been to, this is where your obstacles are, because that is where they put all the temptations, okay, that are there. Now, this is a hospital right next to an obesity unit, but let's leave that alone for a second. But what's on the wall is themed. So clearly, Christmas is just over, so it would have been Christmas chocolates. Now we are a couple of weeks from Valentine's, so it's Valentine's chocolates. Once Valentine's is done, there are Easter bunnies, etc., etc. There's a chocolate for each month, okay? And the whole wall is actually full of them. So this lady in front of me, I was following her behind, being nosy. And so imagine this was a chocolate bar or some lovely treat. Okay, so she picked it up, she kind of looked at it, she went, and she put it back down. Okay, so this whole trip probably took 60 seconds, maybe 90 seconds, okay? She picked up another thing. She put it down. 10 times she was tempted. 10 times she said no, okay? She got to the cash tills. Every time she put something down, in my head I went, woo, quietly, silently. You know, this is the kind of thing that gets you arrested. Woo! So, and then she went up, and so she went up to the cash till. Her guard dropped. And behind the cash till, there's a pimply guy there, right? Selling... waiting to pay for her goods. And then he goes, 2 for 1 cookies? And yeah, for those of you who have been to Stansted Airport or Heathrow Airport at 5 a.m. in the morning for the 45-minute flight to Edinburgh, you're there to pick up a paper and they sell you a iPad-size bar of chocolate for a 45 journey. Anyway, that's my... So the bottom line is she cracked. She walked out 99p for 4 cookies the size of my head. Okay, which is very big, right? So I probably would have said 1,000 extra calories she walked out with, okay, out the door, of calories she did not plan, she had not intended to buy, because that was not her role that was there. Okay, now I'm a human being and I judged. So here's the question: who's to blame? Do we blame the nurse because the nurse was weak-willed, lily-livered, morally bereft? Okay? Do we blame Marks and Spencer's? Do we blame Marks and Spencer's for putting the candy wall of shame up there? Do we blame the government for not making Marks and Spencer's not put the wall of chocolate up there? Now, I don't have an answer for you guys here, and that's plausibly not my reason for being here. But what I do think is that it's a relevant question. Okay, because I don't think that is an unusual scenario I've given you guys. You go pump petrol and you can buy chocolate. You go to Boots to pick up your glasses or whatever you're doing, you can buy chocolate. Okay, this is the food environment we're living in. Who we blame in many ways is neither here nor there. It's a situation we actually have to deal with. Okay, so this is the environment that we're actually dealing with. So, because when we talk about food and when we talk about food intake, and when we talk about body weight and when we talk about body size, we all judge. Why do we judge? Because we think we know about it. When I'm watching the Olympics and I see gymnastics or whatever it is, and you know, someone is doing this, I don't judge because I can't do gymnastics. So I'm watching going, wow, you know. By definition, all of us are experts at eating because we are here today and we are alive. So because of that, we judge. And you know, the way we eat in our families is always weird. You know, it's all very stressful when you go on holiday with someone else's family because it's like, oh, I eat breakfast at 7. No, I eat breakfast at 7:15. Very stressful. So because all of us are experts, we judge. And so it's become a toxic environment. And it is not a new judgment, I have to say. There'll be a strong religious theme. I'm a-religious, but a strong religious theme running through this. These are the 7 deadly sins. Okay, and this is a 4th century religious construct. Okay, so if you do believe, then remember, these are the sins which if you commit, you'll end up on the eternal barbecue, right? So we know this, if you believe. So, and I would like to argue that 3 of these 7 sins can have something to do with your feeding behavior or certainly your body size. Gluttony, Mr. Creosote, all right? Greed and sloth. But in the past, in the 4th century, certainly, there would never have been enough food, all right? So if you were larger than average in the 4th century, you were perceived to have taken food from other people who needed food, thus the sin. In today's environment, does that make us all sinners? That's the kind of question that keeps me awake at night, right? So that I think it's a fair question to ask. I think it's a relevant question to ask, and that pretty much is what this talk is going to be about. This here is the reason why people consider me a bad person. Okay, so this is the church of you. Okay, and all of you would have seen some versions of these scales of balance, but this is otherwise known as the second law of thermodynamics, okay? Which means that you can't magic energy from somewhere, and you can't magic the energy away. So the only way, ladies and gentlemen, okay, that you can actually gain weight is to eat more than you burn. And the only way, okay, is to burn more than you eat. It's the physics. But that is how you become obese. Okay, so I think we're asking the wrong question in very many ways, because how we become obese is physics. Why, however, have we become obese? Why do some people behave differently in this food environment? Why do some people like certain things more than others? For example, as I was following the lady in front of me, I had zero temptation. There was not even one iota of temptation for me to take any chocolate. Now, it's not that I don't like chocolate, it's just that I can either take it or leave it. Now, if it had been a bag of pork scratchings, don't judge me, okay? I mean, I would have had it every day. But that was my weakness. That is something which I like. And you might say, well, what does that got to do with anything? Why? Why do some people prefer chocolate or pastry or pork scratchings or rice, whatever your weaknesses are? All of you know what your weaknesses are, okay? Why compared to something else? There's an argument it could be cultural, absolutely, but there's also a huge biological variation, and I think we need to begin to think that. Now, when you say, well, it doesn't have semantics, it sounds like semantics, you're doing wordplay. It isn't, okay? Because if you actually deal with the how and you're dealing with physics, now if that is the answer, the be-all and end-all, if it's simple physics, then asking people to eat less and move more should solve the problem. Education should solve the problem. Do we actually need more education? If you asked a 6-year-old, don't ask a 6-year-old, but if you could ask a 6-year-old, why do you think that man is fat? Okay, now, like I said, this is the kind of stuff that gets you, a 6-year-old will say that's because that person has eaten too much. If you ask your 99-year-old grandma, or grandpa, both, okay? You know, why is that person fat? They'll say exactly the same thing. We know why we become obese. We know how we become obese. So in other words, education is not going to be the answer. If, however, we begin to understand that where the variation lies, ladies and gentlemen, is in why we behave differently around food, and all of us behave differently around food, you begin to understand that one size cannot fit all. Okay, because if the answer is don't buy any chocolates in your house, Giles, well, it makes no difference to me because I don't like chocolate. Okay, so you need to be able to understand why people do that, and that is where the biological variation actually lies. Obesity is a problem. We know it's a problem. Okay, so this is a map which I'm sure many of you have seen different versions of, and I would say that just two messages I want you to get. Now, clearly, the obesity in what we call the developed economies, Europe, Western Europe, North America, the Anglophone countries, is well rehearsed, okay? I mean, you can't open a newspaper, you can't watch the telly, and you know, documentaries are made by it. I'm responsible for some of them. And then what then happens is you actually see. So that's not what I'm here to talk about. While obesity is a problem, we have not reached the maximum of our problem, okay? Because why? Because of this little corner of the world over here, okay, the Indian subcontinent and China. Now, that's what, a third of the world live there, okay? So, sure, there are probably 300 million Chinese and 300 million Indians who have as much disposable income as anyone here and go on vacation. So these are the Chinese folk, the Indian folk, we all see when we go on vacation, okay? Because they have cash. There are 1 billion Chinese people out in the sticks. There are 1 billion Indian people out in the sticks, where unlike here in the West, the poorer you are, the more likely you are to become overweight. This is a complex question we can discuss later. But in India and in China, at the moment, currently, the poorer you are, the skinnier you are, because you don't have enough food, okay? So, but as these countries become more prosperous, whatever word you want to use, become more developed, in inverted commas, okay, and the governments try and drag these countries out of at least the poor people out of poverty. It come with it the vices, the temptations, the diet. Okay, so we're nowhere near the maximum of this problem, and we've got to really try and think about trying to fix this problem before an additional 2 billion people, okay, become at risk of actually becoming obese. So this is another way of looking at the data. So the data. It's plotting. What is it plotting? So I'm sorry, this is like the L'Oreal ad. This is a bit of science. So what you have here, what you're plotting is BMI, or body mass index. So body mass index is your weight in kilograms divided by your height in meters squared. It's the way to control for your body size, in effect. Okay. And what it's doing is it's plotting your BMI. So above, between 20 and 25 is supposedly normal. This is not perfect. 25 and 30 is overweight, and above 30 is obese, right? And what it has here is it plots the BMI, it plots how many people have it, and it plots males and females, and then in the fourth dimension, it plots time. Okay, and so if you actually have here, and you see what happens in 1984, boom, okay? The average BMI for a male in 1984 was probably around 22 to 23. So the average BMI in 1984 was normal. Boom. 2014, which is where the data has got to at the moment, the average BMI is now 27 or 28. Okay, so the average BMI today, okay, is overweight. Now, if you actually ask the question, as it goes between 1984 and 2014, I look at the crowd, there are some young people here who clearly were not born in 1984, but I think a large proportion of the people here were born in 1984 and have lived throughout this entire change. So let's go back to my title slide. Are your genes to blame when your genes don't fit? In this particular, through that prism, through that question, the answer is clearly no, right? Because this change in our body weight has occurred against the background of no genetic change. We haven't suddenly evolved a second head, right? Evolution doesn't happen over this period of time. So we actually have a situation here where clearly we have become more obese because of the change in environment. And I use that as a hold-all to include socioeconomic class, the type of job you do, how much exercise you take, anything that's not genetic, okay? So, and that's going to be true, okay? That's why we've become fat. Here, however, is the critical point. If you actually look at the histogram, at the graph in 1984, if only the environment plays a role, in other words, if we only respond to the environment and all of us respond in the same way, then the histogram from 1984 should have moved up in its entirety upwards, so that you end up with a shape that looks like the Golden Gate Bridge. Okay, that's if you actually have a shift in BMI 100% to do with environment. But that is not the case, ladies and gentlemen. What you get is you get a change in shape of the histogram. Assuming that everybody alive here was alive here, mostly speaking, okay, it's the case, the only way you change a shape is if everyone in that graph behaves differently when the environment changes. So what we say in the field is, why have we become more obese? We've become more obese because we eat too much, change in environment, blah, blah, blah. We know the answers to that. How obese we become? Do we gain weight at all? That is powerfully biologically determined and powerfully genetically determined. Now, how do we know that is genetically determined at all? A large part of it, not all, but a large part of it have actually come from twin studies. So some of you here may know what twin studies are, but let me précis it just very briefly, okay? So there are identical twins, and there are non-identical twins. So identical twins, for all intents and purposes, are genetic clones of each other. They share 100% of all their genetic material. Whereas non-identical twins, fraternal twins, share as much genetic material as you would with your brother or sister, 50% of genetic material. So you could take any given trait and ask the question, well, if I share all my DNA, okay, and this is a trait, versus if I share only half my DNA, how much do the genes play a role, and how much does the environment play a role? Okay, I'll give you an example. If I had hair, okay, it would be black, and I would like to argue that, peroxide aside, ladies, that hair color is powerfully genetically determined. Age will change it, I understand that, but powerfully genetically determined with very little environmental input, okay? Now, how about on the other end of the spectrum? Freckles. Now, freckles are clearly going to be powerfully genetically influenced, but even amongst identical twins, whether or not they appear, how many appear, will entirely determine, do I like to wear T-shirts? Do I like to stand in the sun? So that's an example of a powerful genetic trait which have a huge environmental influence, okay? So those are almost two extremes you can actually look at. Now, if you do the maths and actually look at it, then the heritability of body weight amongst identical twins, okay, I want to stress, is around 70%. And you can read there, therefore the environmental element is going to be 30%. For some perspective, heritability of height is around 85%. Okay, so it's not as high as height, but it's pretty close. Okay, there's actually a huge genetic influence. And the bottom line is, there is a genetic influence for everything, every single trait of ours. It just depends how much. Okay? It depends on how much of a genetic trait compared to how much of the environment that actually does play a role. Okay? And where there are genes, There are molecules and there's biology to study. And the first real molecular handle, okay, that we actually had and got about there being a molecule so that controls food intake, rather than just entirely a willpower, came from the identification of this obese mouse, this fat mouse over here. This mouse has a naturally occurring mutation in the gene called leptin. Okay, I'm going to spend quite a bit of time on leptin because it really opens up our eyes about the whole process. So leptin is produced from fat, and so the more fat you have, the more leptin you have. Leptin circulates in the blood. It then signals to the brain how much fat you have. I'll come back down and actually talk about this. So this mouse has a mutation in the gene, and as a result, becomes severely obese. Because of this mouse, which was actually identified in 1994, okay, this was the first molecule. We now have a general understanding, a relatively simple framework for how we actually think about body weight control and food intake control, okay? And simplistically put, we have circulating hormonal and nutritional cues. So these can be nutrients themselves, such as glucose, fat, protein, okay? Or they can be proxies for those nutrients. So insulin, for example, is a very good proxy for glucose. It does other things, but it's a very good proxy for the level of glucose in your blood. Critically, these all circulate in the blood. They signal to the brain. Your brain responds and translates and influences your next interaction with food. There are genetic modifiers that run throughout the entire process, which you can then harness. This is the reason why I'm a geneticist. You can then harness these genetic modifiers in order to understand how biology works. Okay? So it was at this point that my colleagues, Professor Ratley, well, Professor Sir now, so we have our lab meeting around a round table. I just understand. I know exactly. Now I'll stop now. So, so Professor Ratley and Professor Faruqi at the time started this, but Steve in particular, Steve Ratley, he asked, I think, a relevant question. So the mouse, as I said, was a naturally occurring mouse that became obese. So Steve asked the question, simply put, is, well, is this just a weird mousy thing? I think it's a fair question. Mice have whiskers and a tail, and we don't have whiskers and a tail, and it doesn't mean that something that happens to a mouse can happen to a human being. But the question was, if a naturally occurring mutation can make a mouse fat, can a naturally occurring mutation make a human being fat? Fair question to ask. Long story short, yes, it can. Okay? So Steve and Sadaf, Professor Ratley, Professor Faruqi, identified these two cousins, and these two cousins have a mutation in that exact same gene called leptin. Now, it's not the same mutation, but it's the same gene, okay? And so, remember, leptin is produced from fat. So what do human beings which don't have this gene look like? Well, I've highlighted you can see the picture. I've highlighted the key points in red, which I'll come back to. So they are born of normal birth weight, so they come out perfectly looking like a normal-sized baby, but then they become hyperphagic after weaning, when they move to solid food. Hyper for more, phagia for eat. Now, hyperphagia is a pathogenic term, so you can't say, I was hyperphagic this Christmas. No, so you guys, dude, you ate too much. So what hyperphagia is hyperphagia is an abnormal pathological eating behavior. These kids have to have their freezer doors locked up because they would have gone in to eat the frozen fish fingers, okay? So now you might think, oh, frozen fish fingers. I'll come back and give you an example where that, weird though it sounds, it's not going to be as weird as it does sound, okay? So you can read the rest, and you can see there's a lot of fat here. They're normal height, okay, so they're not shorter, they're of normal height. They don't undergo puberty, okay, and they have a bit of a wonky immune system, which seems to be an odd thing to bring up in an obesity talk, okay? But it is these last two, okay, that actually have provided really for us a real understanding of what leptin actually does. But before I get there, so leptin, as I said, circulates in the blood and signals to the brain. Okay, so it's a hormone. It's a fat hormone. Now, if we actually take the analogy of type 1 diabetes, for example, where you don't have insulin, and what do type 1 diabetics do? They inject themselves after every meal, around so often, with insulin in order to control their glucose levels. Okay, so once again, this is work done by Steve and Sadaf. They asked the question, well, can we do the same thing with leptin? What happens if you actually inject yourself daily with leptin, like you do insulin, in exactly the same kind of pump that actually goes in? Now, this is a 3-year-old weighing 42 kilograms. Okay, for those Europeans amongst you, you understand how heavy that is. For perspective, times 2.2 for pounds, divided by 14 for stone. But for perspective, I am 75 kilos. So we're looking at a 3-year-old who's 2/3 of my body weight. This is not PlayStation obesity. This is not I've had too much Coca-Cola obesity. There's something wrong with the kid, okay? So, and the kid doesn't have leptin. Look what happens after daily injections of leptin, okay? We now have a child who's 7 years old that weighs 32 kilograms, and you would not bat an eyelid, okay, at this child because he looks perfectly normal. Perfectly normal child now because of daily injections of leptin. Now, at the time, so this picture was probably taken in 2001 or 2002, all right? At the time, the leptin license was owned by the American pharmaceutical giant Amgen. Now, to have been a fly on the wall in the boardroom when the results came in, I think they must have wet themselves. They must have thought, oh, our Christmases in one go, right? Because they thought, we must have solved obesity. Which they hadn't, because it's now 2018, and I'm still here banging on about it, right? So the question is, why did leptin, which some of you may have heard of, but most of you would not have, why have you not heard about it? Why can't you go to Boots and buy leptin, right? And it's not like Amgen actually didn't try. They paid millions for it, okay, because they thought they were going to make trillions. It's not like they didn't try. They gave leptin to skinny people, to fat people, to boys, to girls, to men, to women, to people of all colors. And the universal rule was this. It didn't matter if you had a BMI 18 like Kate Moss, okay? Or if you were BMI whatever like Santa Claus. I don't know what his BMI is, but he's probably pretty big, okay? So, but if you had a functioning leptin system, you did not respond to leptin, at least in terms of food intake. So the question, however, is why? Given that I've shown you if you don't have leptin, you respond to it exquisitely sensitively, okay? So the question is why? We weren't thinking about it correctly. Now, when leptin was first discovered, all of us were bamboozled in the field. Leptin comes from the Greek word leptos, for thin. And so people were thinking, well, if leptin is produced from fat, and if the more fat you have, the more leptin you have, it must act as a negative feedback loop, right? The more leptin you have, it goes to your brain. Then when you have too much fat, it tells your brain to eat less, and then you lose fat. So we thought that it was there to tell you you had too much fat and to stop eating because you're getting too fat. But if you think about it a little bit carefully, when in evolution would we have gotten too fat? When would we have had too much food that we needed to worry about this? Never is the answer. And so there was no evolutionary reason for us to develop something to stop us from eating. So to cut a long story short, leptin does not function when there's too much of it. Leptin functions when there's too little of it, when you don't have enough of it. Why? Because when you don't have enough leptin, you don't have any fat. And if you don't have any fat, you are starving. What leptin's biological role is to turn on the starvation response, okay? What is the starvation response? First thing is to eat, okay? Now, that might seem obvious. All of us know that if we're really hungry, the simplest foods, a piece of bread, some rice, a little bit of cheese, tastes like manna from heaven. It's really delicious, okay? The fuller we become, the more picky we become, okay? This is universal. This is actually what happens. Now, imagine if you were actually starving. Plane crash in the Andes, your partner is looking delicious, starving, okay? Now, would you, if you're actually starving, would you eat frozen fish fingers to keep yourself alive? Of course you would. All of us become hyperphagic when we are starving in order to keep ourselves alive. What else happens, okay? The other thing which happens is your body begins to triage calories for your brain. Now, your brain is about 2 to 3% of the weight and volume of your body, okay? But at rest, such as now, it is using 25% of the glucose that is circulating in your blood. It's a hugely metabolically expensive organ using the glucose up because it does all the command and control. It controls everything that you do, okay, including eating. So what happens is your body begins to save energy and save calories for your brain. What does it do? It begins to shut down metabolically expensive pathways which are not immediately necessary. For example, reproduction, okay? Now, ladies, we know every month, loads of wasted calories, okay? So, but, it's true. But at the edge of starvation, those wasted calories are going to be the difference between life and death, okay? So what happens? Your brain shuts it off. It doesn't allow that to happen. Additionally, if you were actually starving, the last thing you're going to want to do is to plop a baby out into the Serengeti because you're not going to be able to feed the baby. So, like I said, your body just shuts off reproduction. Second thing that's very expensive, and I won't go into in any detail, is your immune system. It's an expensive situation, so your brain also shuts it off. So the question is, all right, is it reversible? Okay, because for it to be a good starvation signal, it's got to be reversible. If it's going in one direction and you can't reverse it, then it's a stupid starvation signal. So is it reversible? Yes, it is. Hyperphagia, daily injections. The child is clearly eating normally now, which is why he's lost all the weight. Reproduction. Remember, this picture I told you was taken in 2000 and something. His older cousin is now a young lady, okay, carried a baby to term. She now has a family, okay. The first leptin-deficient creature, okay, in all of time and history to carry a pregnancy to term because of daily injections of leptin, okay. So reproduction, fixed. And once again, the immune function, that was also fixed. So that, ladies and gentlemen, is leptin's role as it goes away to turn on the starvation response. So I'll cite just a couple more examples. What happens, however, when it signals to the brain? Okay, so when leptin actually gets to the brain, and I won't bore everyone silly. I know that's not the most exciting thing in the world to listen to. But when it actually hits the brain, it hits a class of neurons in a hypothalamus, which is the base of the brain, just here in your nose to the middle of the hypothalamus. Okay, a population of neurons there called the POMC neurons. Okay, so why talk about the POMC neurons? We know that it's important because if a human being has mutations in POMC, or if a mouse has mutations in POMC, we did that work, okay, it results in severe obesity. So I could show you those. But I thought I would go over some more recent data, and this is our work on Labrador retrievers. So just a question, how many of you guys here own Labradors, Labrador owners? Oh, wow, good, all right. Hello, Labrador owners. So this work, by the way, was led by my veterinary surgeon colleague, Eleanor Raffin, okay? And now, the Labradors are the commonest pet dog in North America and in the North America and in the UK, okay? In the UK, there are 150,000 new Labrador puppies that are registered every single year. Okay? I mean, we use it to sell toilet paper, for heaven's sakes, right? So the Andrex puppy. So, but, and I'll point to the Labrador owners in the crowd, leave your compost bin shut, otherwise the Labrador will eat everything within the compost bin. So Labradors are well known to be very, very greedy, food motivated, whatever you want to do. And this is where our interest became, right? Could we identify the biological aspect to its actual feeding behavior? Once again, I'll cut a long story short. The bottom line is, Labradors, as it turns out, have a deletion in this POMC gene. Okay? Now, it's not a complete deletion, only this bit, and not all Labradors have it, which will become relevant in 2 seconds. Okay? So not all Labradors have it. Because not all Labradors have it, you can ask what happens to Labradors with the mutation and what happens to Labradors without the mutation. And so here, this is body weight. And in effect, what this shows here is just weight, and if the dog has no mutation, 1 copy of the mutation, remember we all have 2 copies of every single gene, or 2 copies of the mutation. And you can see here, they get heavier. Each copy of the deletion is worth around 2 kilograms, or 5 pounds, okay? That doesn't sound like a lot until you remember that a Labrador only gets to around 30 to 35 kilos, okay? So this is quite a lot of body weight. What happens to food motivation, food behavior? You'll see exactly the same pattern, okay, where you actually see this increase here in behavior. So if you have the mutation, or if the dog has the mutation, they're more food motivated. Now, is this a dog thing? Because we all know that many dogs will go ruff, 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 and actually eat all the food that is there. So the answer is no. Because we ended up sequencing 38 other dog strains. I mean, Chihuahuas, Shih Tzus, Great Danes, Wolfhounds, everything. No mutation of this in any other dog except for the flat-coated retriever. Now, I'm not a doggy person. I don't know if anyone owns a flat-coated retriever. Oh my God, okay. Hello, flat-coated retrievers. We love you. So flat-coated retrievers are the closest relative to the Labrador, and they're both descended from the St. John's water dog, okay, which is a Canadian fisherman's dog, now extinct. Okay, and so you might say, well, why does this dog have a mutation? So a couple of things. First, not all flat-coats have it either, but when the flat-coats have it, this is the same 2 graphs. That's body weight, and that's food motivation. They have exactly the same phenotype, as do the Labradors. Why is this mutation there at all? Well, the St. John's water dog was a fisherman's dog. Okay, it was bred to jump into the cold water and drag back nets or what have you. in Labrador, which is pretty cold, right? So you can imagine that one day a fisherman was going there and going, there you go get whatever. I can't do a Canadian accent. Go get the net. So, but he probably picked a dog who was willing to go in and get it. A, because it had a little bit of padding around it, okay? And B, was motivated enough to go because he was giving it treats, okay? And so that was probably what happened to the first mutation that was selected for, and it's then kept in the dog strains ever since. So the question is this. Not all Labradors and flatcoats have it, as I said, but they're worth around 2 kilos each. For those of you mathematically inclined, that's around 0.3 standard deviations of body weight, right? So here are the numbers. I don't know the prevalence in the flatcoats, I'm sorry, but I'll look it up. So, calculate it. So what happens here, however, the Labradors is, in pet Labradors, around 20 to 25% will have the deletion, okay, that are actually there. But here's the other interesting thing about Labrador owners, okay? The other reason you have them is because they're lovely family dogs, because of their fantastic temperament. They're fantastic dogs, and they're very trainable. They're so trainable that they are, in North America and in the UK, primarily used as guide dogs for the blind, okay? Now, I think you'll agree that the guide dog is like the Navy SEAL of the dog world, okay? So they go to guide dog camp, and the few, the proud, the guide dogs. And what happens is a lot of failure, because they go up, and those who fail go into the pet industry, okay? But the ones that succeed are then given a human being to look after for the rest of their lives. So very few make it, okay? But the ones that make it are trained within an inch of their life, and they're trained with food, okay? Now, if we look at the guide dogs, okay, in terms of the percentage, 80% of guide dogs have this mutation, okay? So which is odd, because what happens is we started off by studying food motivation, okay, which is what I study, clearly, we've been discussing it the entire time, but have suddenly taken a step into trainability. Okay, so why has this happened? You can imagine a scenario. So if you're trained using food, using standard Pavlovian techniques, then you can imagine here's Fido, or whatever the name of your dog is, here we go, and here is bringing the visually impaired Mr. Smith home, okay? Now, say a chicken runs across the road, okay? So what are your chances of a chicken dinner, right? You're probably looking 80-20, whatever the number is. I don't know what the real number is. I never chased a chicken. But the Labrador is trained to know that it has a 100% chance of getting a dinner if he brings Mr. Smith back home, okay? So when your Labradors have the googly eyes and they're loving you, he doesn't love you, he's hungry. No, it's not true, it's not true. Oh my God, not true, it's terrible. Anyway, dog food heading my way. So we got on the cover of actually this magazine, this journal, Cell Metabolism. That's Eleanor, who did the study, and that's Jasper, one of our participants. Interestingly, chocolate Labradors have a slightly higher percentage of the mutation, and therefore could plausibly explain why they're more, greedy. But anyway, let's leave that alone. So I'm just looking at the time. What happened? I probably have time to go over this. Then there's one other gene, okay? Then I'll stop talking about. No, I won't stop talking about genes. It's only about genes. So what happens is leptin goes, it tickles the POMC neurons, and then POMC neurons have to go on to signal to something else. And they signal to something called the MC4 receptor, or the melanocortin-4 receptor. In the actual chronology of things, this was 1998, and I was a young postdoc, and this was my first paper. Okay, so this is where I appeared on the scene with regards in the chronology. But now you'll be unsurprised that if you have a mutation in the MC4 receptor, which binds to POMC, you're going to be severely obese as well. But this is now, we probably now know that mutations in MC4 receptor are the commonest cause of what we call monogenic obesity, which means that if you have a mutation in the gene, you'll end up being obese. The commonest cause of monogenic obesity ever. Okay, and how common? Was not that common, but it's common. So, for example, if we actually look at people with a BMI above 30, now I'm a BMI of 27, so that's just not that far away from me, right? So, people with a BMI above of 30 have a 1% chance of carrying a known mutation within the MC4 receptor. So you can almost think about saying that MC4 is probably responsible for 1% of the obesity that's out there. The trick is what's happening with the other 99%, obviously. Okay, so it's not common, but 1% is actually quite a lot given the number of people that are actually above a BMI of 30. But my point is this. So this work, just to let you know, this work was done by me as a young postdoc in a lab using cells in a tissue culture hood, right? Whereas this work that was done here was done by my colleague Siddharth Farooqui, Professor Farooqui, in a clinical research facility, okay? Entirely separately. This was done in using molecular findings. Now, the MC4 receptor, we know what binds to it, and we know when it binds to it, we can actually measure the activity of the receptor. So you'd be unsurprised to know, with thousands of different mutations out there, that there are going to be some more severe mutations, and they completely kill the receptor. Okay, you can see here, no activity. That's normal, and these are just all dead. And you'll be unsurprised to know that with a receptor with thousands of mutations, there are going to be some which are a lot less damaging, maybe anywhere from 30 to maybe 70% damaging. This is work that was, like I said, done in a clinical research facility in which they were measuring food intake, buffet food intake. It works better for children, little children, because they don't know they're being watched, not so well for adults, because it's difficult to measure food intake normally in an adult if you know you're being watched. But these were done in kids. Now, these meals are nearly 5,000 calories, okay? And see this control here? My son was one of those controls when he was 4 years old, okay? The most ridiculous thing in the world is to see a 4-year-old facing, what's the critical thing about an experiment? It's got to be exactly the same except for the variable. And the variable here is the genetic status. And so Harry was normal. And so a 4-year-old facing 5,000 calories, it's quite funny. So what did he do? He drank his milk. He had a bite of toast. He threw the Rice Krispies on the ground, and that was it. That was his breakfast, right? So the nurse was picking up all the Rice Krispies, and everything was measured in. Anyway, so the bottom line is this. Here is leptin deficiency. Here is treated leptin deficiency. Okay, you can see the huge improvement. All of the kids with MC4 receptor mutations were tested, in one big batch, and only split up after the lab results. And here's the bottom line. So these are done entirely synthetically, okay? And this isn't done in a lab. The lab results, which I managed to do, predicted how much a child would eat in actually a buffet meal. What does this mean? It means that this is not an on-off switch. The MC4 receptor is not, or the whole POMC-MC4 system is not on and off. It's a rheostat, okay? Because it doesn't matter that whether something is there or not. It depends how many of them are on the surface. It depends on how good the quality of the receptor there is on the surface. It's an entirely tweakable system that is actually there. But those are, as I said, monogenic disorders, which means that you have a single gene causing a disease. There are many other monogenic diseases out there. Muscular dystrophy is a monogenic disease. Cystic fibrosis is a monogenic disease. Leptin deficiency is a monogenic disease, okay? But the vast majority of the BMI problems, which I was showing you at the outset of this talk, have nothing to do, but are not going to be monogenic. They're going to be complex diseases involving multiple genes, multiple complex reasons, interactions with environments that are actually going to be over there, okay? And with new genetic techniques that have actually come on, we now have a better idea of what's going on. So this is Jackson-Pollock diagram over here. You guys forgive me for this. You don't have to read every single gene. That's not the point. There are two messages I want you to get away from this particular graph. Okay, the first thing, I hope you'll see that there are two broad groups of genes. These are genes which are known to play a role in our body weight and our body shape, as it turns out, okay? About 200 genes we now know of. So these genes up here in the pink blob or magenta blob on the top left-hand corner have to do with what we call our waist to hip ratio. So it's the circumference of your waist over the circumference of your hip. And what you see if you do that is it indicates your shape, okay? Do I have a big stomach and a small bum? Do I have a skinny stomach and a big bum? Do I look like a sausage, right? And it looks to your body shape. And your body shape is pretty much, unless you're Arnold Schwarzenegger, pretty much where you put your fat. If you look at a skeleton, the skeleton differs in height, but pretty much looks exactly the same, whereas your fat gives you your body shape, okay? So these are genes which indicate where you put your fat. These genes over here have to do with your BMI, independent of where you put your fat. So these are how much fat you have. First message that I want you guys to take away, where you put your fat has absolutely nothing genetically, okay, with how much fat you have, okay? These appear to be separate. So these, as it turns out, genes of where you put your fat, have to do with fat biology. So how will your fat divide, that kind of question. Whereas how much fat you have has to do with your brain, as it turns out, we know, and in the genes in which we know what they do have to do with food intake. So where you put your fat has to do with your fat. How much fat you have has to do with your head and how much you actually eat. This is another way of looking at the data. This is known as a Manhattan plot, okay? And it looks like a Manhattan plot because it looks like the skyline of Manhattan. Now, this is a gene here which I've studied, sadly, for the past 10 years of my life. Many pain, many tears, okay? But there we go, that's what it is. I only highlight this for one reason. These are not mutations. I want to be crystal clear what these things are. These are single nucleotide polymorphisms, little changes. So half of you here will carry at least one risk copy of FTO. So if you carry one copy, you are on average 1.5 kilograms, 4 pounds, heavier than the person next to you. If you carry 2 copies, you're on average 3 kilograms, or 7 or 8 pounds, heavier than the person next to you. Okay, half of you guys have this. So these are not mutations, these are polymorphisms. All of you will have some mix of any of these genes here. Okay, so why am I bringing this up? Because if you look at these genes, and these, I remember, looked at millions of people now and very subtle changes. What do you see? That is POMC. That is the MC4 receptor, MC4R, and this sits downstream of leptin signaling, the leptin receptor. So these are the same genes I've been talking to you about throughout this entire talk, except if you have very big, severe mutations, you end up being severely obese, whereas little subtle changes into it influence where you sit on the normal distribution of body weight. Okay, so here is a situation. Imagine there are, you have 200 genes or so, okay, maybe 100 genes that you can actually measure. And you can create a risk score, okay, because your genetics is empirical, you can measure it relatively cheaply, and it's empirical, you can create a risk score that is there. And you can have a notional risk, so what is the risk score? You can have 1 copy of each gene, that's a score of 1, 2 copies of each gene is a score of 2, and no copies, which is 0. So clearly your notional maximum for 100 genes is 200, and a notional minimum of 0. But this being biology, we don't have none and we don't have all. We have an average number, and most of us here will have an average number of these different variations of the genes, and kind of shift about here. But here's the interesting thing. When you actually plot the number of these risk alleles you have versus your BMI, you get a linear relationship, which means that the more of these factors you have, the heavier you are likely to get. Okay, so this is polygenics, complex biology, complex genetics in action. But it's more complex than you actually imagine. The number of people who have asked me, oh, that's very exciting, okay, because you can calculate this number. So everyone wants to know their risk score. I want to know my risk score, I want to know my risk score. Why do people want to know their risk score? A, because people want to know their risk score, but they want to know, are they at a risk of becoming obese? Okay, and so people ask me, because I may not be obese yet, but I want to know if I can become obese. So people are asking me, can I find the people over here and predict that they're going to become obese before they become obese? The answer, sadly, is maybe some point in the future, but not yet. Okay, and I'm going to explain to you why. People are now trying to do this. Okay, so I live in a little village. Yeah, it's very posh. In Cambridgeshire, it has 2 windmills, one of which is broken. You can buy flour there. It has 2 churches, one of which is deconsecrated. They're right next to each other. Okay, it's got a pub, and that's pretty much it. But it has someone from Superdrug or whatever actually walking up and posting a genetic test into my door. There we go. Okay, Cambridge. But you can actually ask any number of things that are there, including it can predict how fast you'll run, how much your heart beats, complete. I was going to use a rude word, BS. Yes. So that is there. Why? Because the companies are fundamentally misunderstanding, and how fat you'll become, are fundamentally misunderstanding the difference between population-level risk and personal predictivity. Okay? So what do I mean by that exactly? I'm going to give you an example. This is exactly the same example I give the medical students when I'm actually teaching the first-year medics about the difference between risk and predictability, okay? So just to be clear, these companies are not lying to you about your genetics because that is empirical and they can measure it. And anyway, if they lied about whether or not you had this version or not, you could sue them because then it's just fake advertising. So that's going to be right. They're not lying about where the studies come from. So these are going to be genes which some of us I may have talked about here. They are misinterpreting the data because they don't understand the data. Okay, so I'm going to give you an example about risk versus predictability. Now, this bit is given to first-year medical students, so they're 18 years old. They're embryos. I realize you guys are younger than 18, but forgive me, okay? So they're embryos. Okay, so at that stage, I am talking about the risk of becoming pregnant. Okay? Speaking to an older audience, maybe it's the likelihood of becoming pregnant. But anyway, I'm not judging, right? So, but I think we will all understand that the younger you are, the more likely, the higher the risk of becoming pregnant, okay? And that risk goes down to 0 once you get into menopause and you get to 0, okay? Now, clearly, we have understood this process forever, okay? But, and given the, trillions of women that have ever lived, okay, this is going to be a very robust graph. Yet, can I take a random 34-year-old woman off the street without any biological intervention and predict if she's going to become pregnant? Absolutely not, okay? She could have a 100% chance of becoming pregnant because she's currently ovulating. She could have 0% chance because she's infertile for any number of myriad of different reasons. I mean, you'd be able to tell if you biologically test them for this or that, but based on a risk score, you cannot predict. But that doesn't change the fact that a 34-year-old woman on a population level is about 63% likely to become pregnant. You have to take that same analogy and hold to these complex genetic curves. So while the complex genetics is correct, its predictivity is very, very, very poor. Okay, and that's the difference. So ignore that bit. And plus, you can't get a little bit pregnant. You either are or not. But anyway, we'll live to that. So just 2 or 3 more slides, and then I'll shut up. So let's go back to the question: am I giving obese people an excuse? Okay, and I'm going to argue no. Look, if you consider your genetics, your genes, as a hand of cards. Now, let's ignore the monogenic disorders, because some disorders, once you have, you actually get the disease. But we're talking about BMI here, type 2 diabetes, hypertension, that kind of stuff. You've got to consider your genetics like a hand of cards. You can have good hands, you can have bad hands, and the only people you can blame are your folks, right? So you can't do anything about that. There is, however, you can, however, win with a bad hand of cards. It's more difficult. And you can lose with a good hand of cards if you're silly with the way you actually play it. I'm going to give you another example. I will never, ever run as fast as Usain Bolt. Genes, clearly genes, yeah. But it doesn't mean that if I train, I won't run faster than I do now, okay? I'm clearly nowhere near my genetic maximal potential about how fast I run. In fact, I would say that the only people that are close to their genetic maximum potential are probably professional athletes, because that's all they do. They only train, okay, in order to do that, to try and get as close to their genetic potential as physically possible. What do your genes do? Of course, your genes indicate how you look, what color you are, whether or not you're going to become bald, your likelihood of type 2 diabetes. It gives you a bracket. It gives you a maximum. I don't know about a minimum, but it certainly gives you a maximum range that you can actually go for. But that doesn't mean that within that range, you can't move, that you can't do something about it if you actually understand your biology a little bit more. So, okay, one last thought. Okay, no, 2 last thoughts. Here, the dessert tummy is relevant. So, we know what the dessert tummy is. I think most of you do understand it. But for those of you, just let's recap the dessert tummy, where if you go out for dinner, 3-course dinner type place, okay? Now, I guarantee you, unless you go to a Michelin-star restaurant, let's ignore that for a moment. But if we go to a regular place, by the time you reach your main course, either the middle or the end, you have achieved your metabolic requirements for the day. In other words, you've had enough calories for the day, yet when the pudding comes, chocolate cake, whatever it is, you'll eat it, okay? So that's the pudding stomach. The question is, why is it specific for puddings? Which is always an interesting question, right? So what do I mean? Well, if you say you've had steak and chips for dinner or something, okay? Now, if you've had steak and chips for dinner and you're really full, and the waiter or waitress comes along and says, do you want more chips? Do you want more steak? You go, oh no, I'm gonna puke, right? So we all have had that feeling. But yet, when the chocolate cake comes, you'll eat it. So why is it specific for the chocolate cake? Now we have to chuck back to evolution again. So 50,000 years ago on the Serengeti, this is me, okay? This is me dragging back an antelope. So let's assume that it's cost me 2,000 calories to take down said antelope, okay? Let's just make that assumption. What happens when you get back to the village? You have to eat at least 2,000 calories, right? Because that's what you spent. But if you only eat 2,000 calories, you don't buffer against the time. There's no guarantee you get an antelope next time around. So you need to eat more to make sure that just in case you don't get the antelope the next time around. But so when that happens, a part of your brain known as the hedonic pathway, the element of food, which you get with chocolate cake and not so with broccoli. Sorry, parents, right? I like to find. But anyway, takes over, so you actually eat more than you actually need. But how do you get past the mechanical problem of being filled with 2,000 calories of venison, right? And it's quite bulky stuff. What your brain does is it begins to change the quality of the calories that you like to eat. It begins to increase the caloric density, which means that for every given gram of food you have more calories in it, okay? So you can stuff it in there as much as you can, right? What are high in caloric density? Free sugars. Now, at the time, 50,000 years ago, this would have been honey, this would have been fruit, okay? And fat. Ladies and gentlemen, what is high in sugar and high in fat? Desserts. The dessert tummy is a holdover from the Serengeti, which to make sure you ate as much as possible, even though you were so full that you needed to change the density of the calories so you could stuff as much of it in there as physically possible so that we could live to today, so that we could judge the people who have actually evolved to actually live that. So there we go. That's the thing. So are we all sinners? I guess is the question that we ask. Okay, so this is my last question, where this is me eating a pizza. Am I a sinner? Am I a sinner? I guess, well, what do people who have a high propensity of becoming obese, what is it like? Okay, now, I realize I'm not obese yet, but I have worked with a number of people through television, through what have you, and I've asked them. And simplistically put, both from a biological perspective as well as an anecdotal perspective, okay, people who are obese, who are overweight, people who have a high genetic risk of becoming obese, feel slightly hungrier all the time. Not 10 times as hungry, not twice as hungry, but 5% hungrier all the time, okay? So as a result, they eat more. As a result, they become obese. People say there's always a choice. They're annoying people, skinny people with many, many packs. I have one pack, right? Many packs, okay? Yeah, people always have a choice. They always have a choice. They can say no. Well, okay, yes, they can say no, okay? But if you feel slightly hungrier all the time, it is always going to be more difficult to say no, right? So the one message I want you guys to actually take away from here: obese people are not lazy, they're not morally bereft, they're not bad people. They're fighting their biology, okay? They are feeling hungrier slightly all the time, which is why they are the way they are, and we're trying to fix the problem. It doesn't mean that we can't actually help in getting people to actually lose weight, but until we understand that this is not a moral failing, ladies and gentlemen, it is not a choice that we have full control over, until we understand that, we will never, ever fix this obesity problem, ladies and gentlemen. My name is Giles Yeo. This is where I work. Thank you very much for listening to me.